This is Unit 6, Video 9. In this video we will talk about Dalton's Law of partial pressures, and then we will apply it to an important laboratory setting. So Mr. Dalton is a famous chemist of yesteryear that began studying the idea of atoms, and his name is usually associated with some laws about a definite proportion of atoms, so he was the one that came up with the idea of atom, one of the first to define it. So his name comes up earlier on in your studies, but here he is again with gases. And the law simply states this: the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. So simply put, if I want the total pressure of a bunch of gases, and you put those gases together, you can simply add up the pressures of the gas to get each gas to get the total. Now this is very logical. We would expect this, and it's actually as simple as it sounds. Technically, this is because from the ideal gas law idea, we can treat all gases alike. This is why we can do this. All gases, no matter what the identity of the gas, create the same pressure because we have the same conditions. So air, here we have a cylinder of air, is composed of 5 primary gases. Those gases are nitrogen. Nitrogen is the biggest component. So in this case, we're showing the pressures in both kilopascals and psi. So if we have 78.1 kilopascals, this roughly, the reason why kilopascals is nice, this roughly shows you the percentage of each of the gases in the mixture. So nitrogen is about 78% of the air around us. Oxygen is about 21% of the air. So we have 20.9 kilopascals of oxygen. If the air is not dry, then water will be the next component at 1.28 kilopascals, and then argon, and then you actually have very tiny amount of CO2. A lot of people think that CO2 is the third most common gas. It is not. There's a tiny amount of it, nothing compared to the amount of argon in the air. But what you can do is you can simply add up all these pressures and combine them to find the total pressure of the gas. So it's as simple as it sounds. If you have 5 gases, combine each pressure, and you'll get the pressure of the total. Each of these, by the way, is called partial pressures. So each individual one, these are called partial pressures. So partial pressures are simply the pressures of each part of the whole system, or each gas. Now we're also going to define something called mole fraction. This will be an important idea, and this should say and total. So the mole fraction idea says that we define the mole fraction with the letter x, and it's simply a dimensionless number that expresses the ratio of the moles of one gas to the moles of the total gas. So this is the moles of whichever gas you're studying, this is the total moles, and you simply divide those numbers. And because the units cancel out, whatever the units are, say if it's moles in this case, they cancel out, you have no dimension, or you have no unit for the whole number. So this is a dimensionless number. That's why it says dimensionless. So the idea here is, if we know the mole fraction of a gas, then we can simply multiply the total pressure by that mole fraction to get the pressure of each gas. So if one of the gases is 25% of the whole mixture, we can simply say 0.25 times the total pressure, whatever that is, and it'll give you the pressure of that gas. And that's what this bottom equation shows. So it says that the pressure of that one gas is simply multiplied the total pressure times the mole fraction of that gas. And again, the mole fraction here is just the gas over the total moles. Alright, so we're going to apply this in a problem like this. A study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.25 mole% of carbon dioxide, 18 mole% of oxygen, and 80.5 mole% of argon. Calculate the partial pressure of oxygen in the mixture if the total pressure is 745 torr. So what we'll do first is get the mole fraction of oxygen. Now the mole fraction is simply the moles of oxygen. In this case we have 18 moles of oxygen. This idea of mole percent, they decided to just make everything 100. That's why you see this word percent. But you'll do 18 moles up here, and then at the bottom will be the total moles. In our case, we'll do 1.5 plus 18 plus 80.5. So all three of the gases. So go ahead and do this, and you'll find that this, so let's see, if we got 18, this should be, hopefully, 100 at the bottom. So we got 18 over 100, well, that makes it easy. We get 0.18 as the mole percent. So they make the numbers easy, since the bottom is nice and 100. So what you can now do is find out the pressure of just oxygen. And what we can simply do is take the total pressure. In our case, the total pressure is 745 torr, and then multiply that by 0.18. And this one, go ahead and grab your calculator to do this one. So we got 745 times 0.18 to give you 134 for 3 sig figs. And this would be torr of oxygen. So this is the pressure due to oxygen. And you simply found the mole fraction and multiplied by the total pressure. And that's the idea. Now, where this idea is used a lot in the laboratory is the idea of water vapor pressure. Anytime you collect a gas over water, which is done commonly in the laboratory, what you do is you fill a vessel with water. Here, a beaker is filled with water, and then you perform a reaction which produces a gas, some sort of reaction, and you need to collect that gas. You simply bubble the gas into the water, displace the water, and catch the gas that way. And then what you do usually, you have to make sure that the water level inside and outside line up, and if they line up, then you can assume that the pressure on the outside is the same as the pressure on the inside, and that's the idea. Now, this is not necessarily true, because what happens, unbeknownst to most people at first, is that the air inside of here, or rather the gas that was collected inside of here, say this is a red gas, some sort of gas was collected, has mixed in with it another gas, and that other gas is good old H2O. So a little bit of water vapor is actually mixed in, and this is impossible to avoid because you're actually collecting it over water, and water always evaporates. Because water always evaporates, there's a little bit of gaseous water in any place that has liquid water, essentially. So what happens is this water pressure, some of this pressure is actually due, the pressure of water, has to be subtracted away from the total to find the pressure of just the gas. So if I want the pressure of just the gas, whatever gas I'm collecting, I have to take the total pressure and remove the pressure due to water, which would mean that our pressure has to decrease by a certain amount. Now, water vapor pressures have been calculated for every possible temperature that's relevant, and we have tables like this. So you'll notice that at every temperature, say at 10 degrees Celsius, there is about 9.2 millimeters of mercury of water vapor in there. Now, at room temperature, which is about 20 to about 25, there is anywhere from about 17.5 to about 24 millimeters of mercury of pressure. And that's actually significant enough to alter our lab results. So this is an important amount, not a tiny amount to ignore. And you'll notice that the higher the temperature, the higher the vapor pressure. At 100, the vapor pressure actually reaches atmospheric pressure. So the higher the temperature, the more this effect takes place. But we cannot ignore it. So what we'd have to do is find our temperature, say if we're running our experiment at 22.5, and we have to subtract away this much pressure from the gas that we're measuring. And we're going to do exactly that in this example problem. So we have a sample of KClO3 potassium chlorate, partially decomposed, producing oxygen gas, and this is collected over water. The volume of the gas is 0.250 liters at 26 Celsius and 765 torr, and how many moles of oxygen are collected. Now, usually we make, this is a simple PV&RT problem, because we're asked how many moles of gas. We're given pressure, temperature, and volume. And let's go ahead and solve for that. However, we have to realize that the pressure here has to be adjusted. So this pressure of 765 torr is not the actual pressure of oxygen. since this is collected over water, there's some water gas in there. So what we have to do, our pressure simply gets adjusted. Our pressure is actually going to be 765 minus whatever the pressure is under 26 degrees Celsius. So if we go back up to the previous slide, we see that at 26 Celsius, all the way down here, we have 25.2 millimeters of mercury. So we'll have to subtract away 25.2 from this amount here. And that's the idea. So 65 minus 25 is 40, and then so 39.8, so 739.8 torr, or millimeters of mercury. So that looks like that is our pressure that we'll have to deal with. And that's really the only adjustment you have to do. The rest of it, simply plug it in to the PV and RT equation and solve for moles. In this case, N is PV over RT. And I'm going to, I'll have to convert torr into ATM in order for me to use the R. That's 0.08206. So let me do this a little quicker. What you could do is we'll obviously have to convert torr into ATM, which means we have to divide by 760. So what I can do actually is 739.8 over 760. This is the conversion factor that divides to get to atmospheres. And my volume is 0.250. Looks like my R is 0.08206. And finally, my temperature is 299 Kelvin. So if you plug this in, what you'll get, let's do this, 739.8 over 760 times 0.25 over 0.08206, and also divide by 299. And you get yourself, looks like we have 2 sig figs, nope, 3 sig figs. The temperature in Kelvin still gives us 3, so we get ourselves 00992 moles of oxygen gas, which would be different if we forgot to subtract the pressure. Now ask yourself, if we did not subtract the pressure, if we forgot to subtract the pressure, would your error be higher or lower than this? Well, if we didn't subtract the pressure, then this number would be higher, which means we have a higher number on top, then your oxygen moles would be higher. So if you didn't do this, you'll show too much oxygen having been caught. And what happens is some of that gas that's been collected is actually water vapor. So if you remove that, well, it makes sense that we actually have less moles of gas. All right, this wraps up video 9 for Unit 6.